Okay, Unit 12, Target 2, using segments within a circle to solve. So, I highlighted this bottom portion of our graphic organizer. There's a tangent line, JK, and a radius, LG. And the point is that the radius and the tangent line are going to be perpendicular to each other. We actually have a theorem or property that says that. It says, in a plane, if a line is tangent to a circle, then it's perpendicular to the radius. That means that anywhere I could draw a tangent line to the circle, just going to draw some lines, then move them to make them tangent. Means I could also draw radiuses, or radii, and they would be perpendicular at the points of tangency. So this would be a right angle, this would be a right angle, this would be a right angle. So anytime I have a tangent line and a radius connected to each other, I know I have a right angle. Because of that, if I go back and look at this, I'm going to have right triangles that can be drawn. With the right triangles, our strategy then is to use the Pythagorean theorem. So here's one of the notes from class. Is BC tangent to circle A? And there's a hint. Hint says, what do we need to know about a triangle? So if this was a tangent line, our theorem says that the only way for this to be a tangent line, and by this I mean BC, the only way for BC to be a tangent line is if it is perpendicular to the radius. Well, how do I know if it's perpendicular? I use the Pythagorean theorem and see if the Pythagorean theorem works. 5 squared plus 12 squared equals 13 squared. So 25 plus 144 is equal to 169. We're trying to see if this is true. On the left side, 25 plus 144 is equal to 169. So 169 is equal to 169. That means it is in fact a right triangle. And because it is a right triangle, that means that yes, BC is a tangent segment. If it was not a right triangle, that means it would not be perpendicular and it would not be a tangent line. Now, another problem I like to do with this problem is to look at it another way. And so what if we knew that this was a tangent line, but we didn't have this 13 given? And instead, which 13 was the entire thing from A to C, instead we had x. And x only went to that point and then to C. So we were trying to find out what x was. So the question would be, if I knew that the radius from A to B was 5, and I knew that B to C is 12, how could I find x? Well, I could do the Pythagorean theorem because I know that the radius squared plus the tangent squared is going to equal the hypotenuse squared. And so when I get to 169 and I take the square root, I'll get 13. So I know the entire thing is 13. We could find that. The question is still, how do I find x? Well, one of the things that you need to start to look for is the fact that a radius is going to show up in more than one spot. And so if the radius is 5 in the circle, the radius is 5 in the circle everywhere. And so A to this intersection point is also 5. And so if the entire hypotenuse is 13 and that part is 5, then x is going to be 13 minus 5, which is 8. Here's a problem that's similar to using that. In circle A, B is the point of tangency. And we're trying to, come on, there we go. We're trying to find the value of x. Well, this problem is very difficult to do unless you recognize that this radius has to be the same length as a radius anywhere in the circle. And so if the radius is x, I can put that on both parts of the triangle. Now using the Pythagorean theorem, I have one leg squared, x squared, plus another leg squared, 8 squared, is equal to a hypotenuse squared, which is x plus 4 squared. So on the left-hand side, I have x squared plus 64. And on the right-hand side, I have x plus 4 times x plus 4. you need to be really careful how you work out that quantity squared. On the left-hand side, I have x squared plus 64, and on the right-hand side, I have x squared plus 4x plus 4x plus 16. So x squared plus 64 equals x squared plus 8x plus 16. And now I can start to solve. To do that, I can subtract x squared on the left, subtract x squared on the right. 64 is equal to 8x plus 16. And working this out all the way, you should get x equals to 6. So that's one main theorem that comes from working with segments in the circle. So a tangent line and a radius are always perpendicular, leads to problems using Pythagorean theorem. The second theorem has to do with two tangent lines. So on your graphic organizer, you had two tangent lines. Okay, if two tangent lines intersect at a point outside the circle, like J, then the distances from the point of tangency, G and A, to the intersection point have to be the same. We have a theorem that says that as well. So theorem, tangent segments originating for a common external point are congruent. I'm going to prove this in a second, but I want to show you an example really fast. So here's an example. I have a tangent on both sides, and the theorem says that those tangents have to be congruent. So 28 equals 3x plus 4. But a lot of you guys learn better if you know why that's the case, where that comes from. So we draw a triangle. And the idea is if we can prove the triangles are congruent, the top triangle and the bottom triangle, then we can show that those black segments, those tangent lines, are congruent. So in class, we talked about how do we prove that's congruent? Well, we know AB and AC are congruent to each other because they're both a radius of the circle, and the radii have to be the same. We know that segment AD has to be congruent to itself, so we have side, side. And we just learned that a radius and a tangent have to be perpendicular. So we have side, side, right angle, or hypotenuse leg congruence. So with hypotenuse leg, two right triangles, the hypotenuse and a leg of one triangle are congruent to the other. Now that the triangles are congruent, we can say that their corresponding parts are congruent. So that's a brief summary of target 2 for unit